advanced energy vehicle resembles the B-2 bomber both in looks and in flight style. The process to build both started in the same ways.
Brainstorming, sketching, constructing, and testing.
Brainstorming for our AAV began by selecting success criteria. In order of importance, these were balance, directional acceleration, durability, maintenance, center of gravity, aerodynamic ability, and cost.
Each of us made a 3D drawing of a concept that was based on success criteria. The team collaborated to make a new vehicle based on a combination of all of our individual designs.
Sketch 1 was durable and the parts were easily accessible, so it was low maintenance.
Sketch 2 performed well in the categories of balance, aerodynamic ability, and directional acceleration, but poorly in the categories of durability and center of gravity.
Sketch 3 proved to be balanced and aerodynamic because of its use of symmetry.
Sketch 4 excelled in balance and in the center of gravity, while it lacked directional acceleration and had high maintenance. Sketch 5 proved to be proficient in balance, durability, maintenance, and center of gravity. This design scored the highest and was created in SolidWorks.
The early design was improved upon as more parts were added, following the constraints included in the operational requirements. At most, 2 motors and the size constraint are included. Then the vehicle was constructed.
Weekly tests were conducted to improve upon the initial design. The optimal propeller was found using a wind tunnel, and an alternate vehicle was constructed. Workdays involved writing, testing, and perfecting code in order to use the least amount of energy possible while still completing all tasks.
The AAV was tested on the desktop track and then on the overhead track. On the overhead track, the AAV must start with at least one wheel on the black tape, travel to the station, stop with at least one wheel on the tape, continue and attach to the caboose, and return and terminate at the station, ending with at least one of the caboose's wheels on the tape.
Problems were first encountered when attempting to attach the battery and Arduino to the AV. This was resolved when brackets were added to the back of the cross shape to affix the battery onto the vehicle, while the Arduino was connected underneath of the foundation. Writing the code to produce the least number of joules proved to be another obstacle. Short surges were applied to the motors in order to use the lowest amount of energy possible. No reverse commands such as braking were used because this greatly increased the power. As the power decreased, the program had to be changed because the power or the number of marks had to be increased. We overcame this by performing our final test after our program wrote for our first time.
The vehicle proved to be successful in our first test run. Although we had previously achieved 30.75 joules and a ratio of 115.6 joules per kilogram, our final testing was 32.84 joules and a ratio of 121.2 joules per kilogram.
The design process led to the final AAV model because of the steps we used to get there. Each performance test helped determine flaws in our design and helped to optimize the code. Without the performance test, our AAV would not have been as efficient as it was.
Overall, this project taught us about the steps required to complete an entire work project from beginning to end. The methods of brainstorming, sketching, constructing, and testing will be used in all future projects.
By participating in the AAV project, we learned how to manage our time accordingly to deliver a fully operational device fulfilling all intended objectives in an optimal format. Our team cooperated correspondingly and used a trial and error process to arrive at a peak performance and to maximize our results.
This project would not have been possible without the help of Dr. Bill Schlosser and the graduate and undergraduate teaching assistants in the Green Engineering Scholarship.